Okay, now we continue with chapter 7. That is about the Anova model. Okay, first of all, to give you the general concept about the model, I give you a few seconds for reading example 1. Okay, focus on example 1. Okay, so in this example, we're interested on the effect of the Harwood concentrations. Okay, the effect of the Harwood concentration on the tensile strength of the paper product. Okay, the Harwood concentration. Okay, so in reality, the researchers will classify the papers into 4 different levels of Harwood concentrations according to 5%, 10%, 15%, and 20%. Okay, they decide to make up 6 test specimens at each concentration level using a pilot plant. All of 24 specimens will be tested to record the tensile strength of the paper. Okay, and here we have the data set. We have totally 24 specimens corresponding to different levels of Harwood concentrations. For example, number 8 here, indicating that the second observations in the first group of Harwood concentration will have the tensile strength is H size. Okay. The question now is that does the Harwood concentration affect the tensile strength of the papers? That's our interesting question. Okay, that's the initial hypothesis that I always asking you on the second step of the data analysis. Do you remember? In the second step, once we have the data, the second step is to find the initial hypothesis. It means that the beginning questions, the expected questions, what we want to make conclusion. So here, starting from the data set, about 24 tensile strength of the paper according to different levels of Harwood concentration. We are wondering whether the Harwood concentration really affect the tensile strength of the paper or not. This question equivalent to say that in the statistical approach, it means that we are comparing the tensile strength means between 4 groups of Harwood concentrations, right? We only able to compare the means between different groups. And if there is the difference between the average tensile strength of the given 4 levels of Harwood concentration, it means that the Harwood concentration really affect the tensile strength of the paper. If at the end, if you use any statistical approach and we found that there is no differences between the average tensile strength of different groups of Harwood concentration, it means that the Harwood concentration doesn't affect the tensile strength of the parts. Right? This is our question. This is our initial hypothesis. And we want to have the method that helps us to answer for this question. Maybe some of you already recognize that it's just the question about comparing the means of different groups. But how to do? So far, we only know the hypothesis that in case that we compare one population mean with the constant. That's the knowledge of chapter 5, right? And then we also know how to compare how to do the comparison between two means of two populations. That's the knowledge of chapter 6, right? But now the question is that we have more than 2 groups. Especially in this case, we have 4 groups corresponding to 4 levels of Harwood concentrations. So of course, the knowledge we have learned in chapter 4, chapter 5, and chapter 6 is not enough. We need a new tool. We need the new statistical inferential approach that allows us to make the comparisons between the means in case that we have more than 2 groups. Okay? And in this chapter, we introduce the method that is called the Anova model. Okay? The Anova model is another statistical inferential approach that allows you to make the conclusion when you have the target of comparing more than 2 means. Okay? When we work with any model, of course we need to know the data set we are using. Okay? In case of Anova model, always the data set must conclude. The data set must include at least 2 random variables. Okay? We must have y. Y is the output variable. The output variable or the dependent variable. Okay? The output variable or dependent variable is just the quantity that we want to model. For example, in our case, the output variable will be the tensile strength of the paper. Okay? And of course, unit S will be the factor variable. The factor or independent variable. Okay, and the factor variable S must be the categorical variable. The categorical, it means that S will be S will classify the output variable into different levels, or different groups. Okay. So the categorical S can be quantitative or can be qualitative. Okay, qualitative it means that you can measure you can explain it numerically. For example, in our case, S indicates the level of Harwood concentration: 5%, 10%, 15%, and 20%. That is the quantitative categorical variables. Okay. Now suppose that I'm interested on how different time of the day can affect the concentration of students. Okay, the studying concentration of students. Suppose that I have the scale to measure the concentration of students from 1 to 10. Okay, and then in our case, because I want to modeling the concentration level of student, so y will be the concentration level of student, right? And s must be the categorical variables. So I left s will be morning, afternoon, and evening. Suppose that I want to see whether different time of the day will affect the concentration level. So in this case, S will be morning, afternoon, and evening. That's the qualitative variables. Okay. So anyway, to use the Anova model, basing on the target that we want to compare the means of different groups. Okay. Hence, of course, you must have the random variable S, which is the categorical variables, which classify the output variable Y into different levels or different groups. Okay. Return to the slides. Here, that is the typical observed data. You will see that the first column I indicate the treatment. The treatments is mean that the factor variable S. We have treatment 1, 2 until K. K treatments corresponding to K levels of the factor variable S. Okay, and then the observations. For each treatment, we observe n observations. Generally, the number of observations belong to different treatments can be different. But to be easy, okay, in the easiest case, I only consider in case that we have n observations for every treatment. Okay. I chose this situation to teach you. It's just because it is simple. Okay, but you can remember in your mind that in general it can be different. Okay, and of course, given the number of observations like this, so the total observations will be n equals to nk. Okay, and you can find the sum of output variables for different treatments and the total sum. Okay, and also easily you can find the sample average for each group. Okay, let's see the data. The next question. Now, what is the model? We already know the target of Anova. We already know the type of data set suitable for using. And now, lastly, we need to introduce the model. Okay. Here, in Anova model, we consider its observation Yij equals to mu, which is the overall mean. Tau I is the treatment effect, and epsilon Ij is the random error component. Equation 1 is really important. It indicates the general concept of the model. The title of the method is the analysis of the variance. The analysis of variance. What does it mean? What does it imply? What is the variance? As I told you that the variance indicates the variability. It means that how much difference from observation to observation, right? And our analysis of variance, it means that we try to understand why there is the differences between observation in two observations. It means that we want to know what is the regions that make the variability in the observation Yij. Okay. So, wait. So we have the model. Yij equals to the general mean plus tau I plus S long I j. Okay, can you recognize that this equation, the parameter mean, this is the overall mean, the overall average, the overall average. The overall average, it doesn't depends on the index ij. It means that any observations will have the same overall average. Okay, and then the second parameter is tau I. Tau I is the treatment effect, because I indicate the treatment I. Okay, I indicates the treatment I. It means that rough I, treatment I, and then j indicates the observation. Okay, so tau I is mean that the means will be different from treatment to treatment due to the treatment effects tau I. Okay, if there is no tau I, it means that all of observation belong to the same group will have the same output variable. But now due to there is the treatment effect, the treatment effect is mean that belong to different group of the factor S. Will list to different values of the output. Okay, this is the treatment effect. Okay, moreover, look at the data set. We can see that the tensile strength is not only different from different levels of Hawood concentration. It's also different even if they are belong to the same levels of Hawood concentration, right? It means that besides the treatment effect, there's something also affects the output variable Y. Okay, it's really realistic, because in reality there's so many factors that also affect the tensile strength of the paper. But in this model, we only consider the Hawood concentration as the main factor. It means that we ignore all of the other things that also affect the tensile strength. In this case, we assume that all of the other factors that also affect the tensile strength will be the random effects. Okay, and the random effect will be the factor that make the variability, or that makes the differences for observation belong to different levels of belong to the same level of Hawood concentration. Okay, we will return to this equation later. Now we arrive to some assumptions of the model. Any model to use this, we need to know the assumptions. Okay. Few minutes. So in the equation 1, if we consider mu I will be mu plus tau I, that is the mean of the I treatment. Okay, this is the true average of H treatment. Okay, and then in Anova model, we consider H group will be one population with the mean equals to mu. Okay, and then the random error S long ij will follow normal distributions with the same variances sigma square. Remember that we have the constant variances sigma square for any observation, even they come from the same or different group. Okay, and here it's important to remember that all of the observations belong to different groups will be considered as the population. Okay, because it's really relating to the hypothesis test of two populations, as we have learned in chapter 6. Remember? In chapter 6, we are given population 1, x1, x2, and 2, xn. And then in population 2, we consider the random sample y1, y2, and 2yn. Similarly, now we have k group. Okay, we have group 1, group 2, and 2 group k. So we have the number of observations y11, y12 until yn came from the first population, that is group 1. And then in group 2, we have y21, y23, y22, y23, and so on. Each observation belong to each group will be considered as one population. And all of the populations here will be assumed to be normal distributions. Okay, I hope that you will recognize, you will have the feeling of familiar. Okay, so in chapter 4, chapter 5, and chapter 6, always, firstly, we can consider the random sample come from population. And then we assume that the population follow normal distributions. Then we consider Z test or T test, right? That's what we have learned in chapter 4, chapter 5, and chapter 6. Now similarly, the Anova model, it's just different that now we consider more groups. It means that we consider more populations, that's all.